Hey, hey, it's a brand new day, and I'm Dr. J. Today we're going to do some limits, more limits. It seems to be the topic of this course and this chapter especially. Today we're going to focus at limits at infinity. Focus on these two types of limits. So as x is approaching infinity or as x is approaching negative infinity. These are the two types of limits at infinity. In algebra, we didn't use the word limit. We called this, so if you've taken my algebra course, you've probably already seen this before. We called this the end behavior. So we could calculate or, predict, I guess is a better word for it, what direction the graph would be going at the end, the two arrowheads, sort of like one arrow points up and another arrow points down or something like that. We call that the end behavior. We're going to be more calculus-y, that's a word, in this lecture about it. So let's just get right into it with some limits at infinity. So you may recall that there are a couple theorems. One of them, I didn't really name it as a theorem, but it is a theorem. It's what's called the direct substitution theorem. Yeah, so you heard me say that a lot, direct substitution, and it applies to polynomial functions. So if f of x is a polynomial function, this is what's called the general form of a polynomial function of degree n. Okay, so this is a polynomial function of degree n. An is the leading coefficient. Sometimes we just call it a, but I'm using a subscript an to indicate that it's the coefficient of the leading term, and the power or the degree is n. All right. So anytime we had a polynomial function, when we wanted to find the limit at a value, like c, it was very easy. We simply plugged in c. Yeah, we call it the direct substitution theorem. All right, and I demonstrated that over and over again in lots of different examples of that. We're not going to be doing a lot of that today, but we still will do it when it applies. We will definitely take advantage of this fact. So when we have a polynomial has infinite domain. You can plug in any number you like. You're never going to have division by zero with a polynomial. You're never going to have to worry about square rooting a negative number or anything like that. We call it a well-behaved function. Yeah. Then if you want to take its limit, you just plug in everywhere there's an x, you plug in whatever the value of c is. Unfortunately, infinity and negative infinity are not values, right? So we can't just plug them in. All right. So, this theorem only works when c is a real number, right? C is a real number. But infinity and negative infinity aren't numbers. Yeah, so we have to sort of be a little bit more creative about how we plug them in. So we're going to have another theorem. Yeah. This is the theorem on the end behavior. Again, f of x is a polynomial. I'm not going to have room to write that. I'm just going to have to copy it one more time. So f of x is a polynomial. The dot, 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 of course, just means all the in-between terms. I'm writing this in what's called descending powers order, or simply descending order. So the end behavior is what the limits, these two limits, look like. I'll start with the right end behavior. So the limit is x goes to infinity. Sometimes I start on the left, sometimes I start on the right, sometimes I don't care. I might only just ask for a particular one. So we're going to the right, to positive infinity of f of x is equal to the limit of the leading term. And that is very, very useful. All right. In algebra, and I'm not going to do it again, but if I made a table of values, right, an XY table, right, where Y is the output, X is the input, and I took a big function like this, and I'm going to do one with actual, numbers in a minute. This is the general form. And I plugged in progressively larger values of x. So I plugged in 100 and then 1,000. I think I've done it before, right? Not with this function, but you've seen me do that. You plug in 100, plug in 1,000, plug in 10,000, plug in 1,000,000. Just keep getting larger and larger and larger. You'll see that the whole function, using all of the terms, ends up being approximately the same as just looking at the leader. Right? I mean, you can kind of think of that intuitively. When you get up into the millions and the billions and the trillions, these little terms are so small, right? I mean, these are units, basically. These are just tiny. I think of it like money. This is like the change, right? Or the single $1 bills, right? And if you got millions and billions of dollars, right? This is a business class. At some point we will revert back to the concept of money. It's coming, right? I have to lay the foundation first. Then there would be insignificant figures, right? So all we would really care about is the leading term. And it turns out that these limits are the same. Okay. So when we do a limit, whether it's going to infinity or whether it's going to negative infinity, we can just look at the leading term, and that's how we're going to calculate our limits. All right, so let's do an example. The limit as x goes to infinity of 5x squared minus 3x plus 2. I don't have enough room to do the whole thing, so I'm just going to do this one. I'll do the negative infinity in a second. I want to leave this theorem up here for a minute. So we can take the limit as x goes to infinity of 5x squared. Yeah, that's the an x to the n here. I don't have to look at the entire, all of the entirety of the rest of the terms. I can just look at the leading term. All right, so let's think about it for a second. We can think about it graphically. Today, I probably won't use my graphing board too much. I've got an example in a little while where I'm going to need more detail. But, I mean, if I don't need all that detail, it's just a very general function. 5x squared looks like this. It's just a parabola. It's probably skinnier than this, right? If you remember from algebra, the leading coefficient kind of determines how skinny it is. All right, so as x is going to infinity, this value is going also to infinity. Yeah. In other words, the right-hand side, I don't know if I like that color. Let's switch colors. The right-hand side, or the right end, is going up. All right. Now, it never actually equals infinity, so we will say the limit approaches infinity. I'm still using that to indicate that the limit does not exist. I'm just going to put DNE technically. All right. But I don't want this homework to have a whole bunch of DNEs. I mean, there might be some. There'll be some cases where I do want you to put DNE, and I'll explicitly say, enter DNE if it doesn't exist. For these ones, I don't just want you to have a whole bunch of problems where they're all DNE, because that's essentially what would happen. You're going to have a lot of infinities and negative infinities, and I want to know which one it is. And so in order to get you to analyze it and tell me which one it is, we don't use an equal sign, we use an arrow. All right. So that's it. That's the theorem, and we're going to be using this theorem for several different examples. Let's continue with this example. I guess I could just continue up here. The limit as x goes to negative infinity. Let's do the same one, 5x squared minus 3x plus 2. Again, that's going to be the same as the limit as x goes to negative infinity of just 5x squared. All right, so now we're looking at this side. So this is as x goes to negative infinity on this side. Well, it's still going up. So this approaches positive infinity. The limit approaches positive infinity. And again, if I really wanted to be technical, I would say the limit doesn't exist. Right? It doesn't actually equal a number, but it has a tendency to approach a larger and larger value. Notice what I don't do is I don't just plug in infinity and just say, it's infinity squared or something. Because that doesn't really mean anything. I mean, you can plug in a million, and say a million squared. You can plug in a billion, but you can't actually plug in infinity. Right? You'll never actually get there. Right, so the right-hand side is as x approaches positive infinity. And the left-hand side is as x approaches negative infinity. So what we should probably do before I do another example is a quick review of power functions. That's what these things are called. So we'll say an x to the n. Just a quick review. It'll only take a minute here. So if an is positive and n is even, essentially looks like a parabola. Yeah, not exactly, yeah. But, a fourth power basically has the same shape as a second power and a sixth power and an eighth power, all the even powers. If an is negative, again, this is a quick algebra review, and n is even, well, then it's an upside-down parabola. Generally speaking, it has that basic shape. All right. There are some slight differences. If you remember in my algebra class, if you took my algebra class, as the power gets larger, it starts to get a little flatter down here like that. All right. So you could just say, well, we don't really know that behavior. We're just looking at what happens to the arrows. So they're both going down. All right, because you don't really know what's happening in here. We'll get to that later. All right. So all power functions fall into these four categories. If an is positive and n is odd, you remember this, right? The right arrow goes up, the left arrow goes down. And again, we don't really know what it looks like in the middle. It depends on the particular values that you have in your function. It depends what these numbers are. And then the last one, if an is negative and n is odd, well, then the left arrow goes up and the right arrow goes down. And again, you don't really know what it looks like in the middle, but you do know what it looks like at infinity and at negative infinity. So example 2. Let's do the limit as x goes to infinity of negative 3x squared plus 4x minus 5. That's going to be equal to the limit as x goes to infinity of negative 3x squared. Which category are we in? An is negative. Yeah. It's technically A2 because the power is 2. And n is even. N is 2. I can just generally call them an and n. But I know that n is 2, so this is A2 and 2. Yeah. I don't want to have to say that every single time, so I won't. All right. So that means we're in this case. Yeah, so both arrows go to negative infinity. Yep, they're both negative infinity. And again, it doesn't equal negative infinity. We say it approaches negative infinity. And they're both going to go to negative infinity. In this one, they both go to positive infinity. For this one, that's a terrible looking infinity. Let me try that again. Yeah. In this one, you get one of each. You get a positive infinity and a negative infinity, and vice versa. Negative infinity and positive infinity. So you get one of each in these ones. So that's your quick review of power functions. If you're looking for some easy homework this week, this is going to be your time to just knock out some points without really doing a whole lot of busy work. So both of these limits will be equal to negative, will approach negative infinity. So it kind of looks like this here. They both point down. All right, I'm not going to do very many of these, and we're going to get into the more complicated ones, but these are the sort of the introduction to limits at infinity. You should be able to do the rest of them just by reading them carefully, not really doing a lot of calculation. So these are really just reading exercises. How about 2x to the third plus 4x squared minus 9x plus 7. Limit as x goes to infinity. Again, all you care about is the leader, largest power. So that's positive and odd. So that means the right arrow, so this is the right side, is pointing up. Yeah. When I lift my right hand, you see it on the left side of your screen. So I mean, if I lift I'm opposite here. Okay. Let's do them both. The limit as x goes to negative infinity then. So this is the left side of the graph. Well, this is again, an even, I'm an odd power, third power, and a positive leading coefficient. So the right arrow is going to go up. It means the left arrow is going to go down. The only thing I might do to try to, make sure that you're reading this carefully is to hide the leader. Sometimes the leader hides behind the other terms. So notice the leader is not in front. Yeah, the leader is hiding right here. Make sure you include whatever the sign is. It's pretty obvious when the leader is out in front, but when the leader is hiding, you got to be careful. That's not a 9, that's a -9. So again, you have a odd power, but you have a negative leader. So that's going to go to negative infinity. As x goes to infinity, this function will go down to negative infinity. The cool thing about the odds, well, I guess they're all kind of cool once you have it figured out, but if you know the answer to one, the other one's just going to be the opposite. That's with the odd powers. With the even powers, if you know the answer to one, then just copy it. That'll be the answer to both of them. So this one will be the opposite. Which is really kind of what an odd power means, really. It's one of the reasons why we call it odd, It's opposing. Yeah, these are opposing each other. As opposed to even. Even is like, they're matching each other. They're even. They're both going in the same, like a pair. Yeah. Another word for that is parity. Yeah. So odd parity versus even parity. Let's do one more. In the United States, and not just the United States and several other countries, I'm not going to list them all out, we have sort of standardized putting the leading term out in front. Okay? And sometimes we'll call that standard. But it's really not a worldwide standard. It's a local sort of policy. Yeah. This is another standard that you might see in other parts of the world. Okay, it just really depends, the context and where the book was written. It also could just depend on the author of the book. So some authors prefer the opposite order, where the leader is at the end. Yeah. Although, again, is this really the end? Maybe it's the beginning. If you're reading it this direction, this could be the front. Yeah. So be careful. Find the largest power, and that's the leader. That's a negative. So we have a negative coefficient. Technically, it's a -1, and then an even power. So that means both of the limits are going to negative infinity. And you can just copy it for the other one. Blah, blah, blah. Same function. Same leader. And it's going in the same direction because the power is even. Okay, so that's polynomials. Polynomials are probably the most well-behaved function that we will see in this course. Next, we'll talk about rational functions. Rational functions are all sort of descendants of the classic reciprocal function. So they sort of all have their genesis in the reciprocal function. I'm just going to use y because it's a little bit easier. Y equals 1 over x. Now, they're not all this simple, but they all kind of come from this basic form, where there's a variable in the denominator. They're going to get a little more complicated, but we'll start with the simple ones, okay? So, example 6. Let's take a basic reciprocal function and multiply it by 8. All right, so we have some kind of a constant. The easiest constant is clearly just 1, but you could have other types of constants. All right, what happens as we go to infinity? All right, what happens to this thing? Now again, I usually start off with an equal sign, and then I have a couple choices. If the limit doesn't exist, I can put equals dne. If the limit goes to infinity or to negative infinity, then I can use an arrow and say it approaches infinity or negative infinity. And then if the limit exists, it actually equals a number, then I'll keep it as an equal sign. That causes a little bit of an annoyance for the reader. We have to be very careful with how you're writing it and how you're perceiving it. But I might amend that concept as we move forward in this course, because it's going to start to kind of drag on us to have to constantly switch back and forth between the different notations. But if we want to be precise, we have to have all of that well documented early on. All right, so the limit of x goes to infinity of f of x. All right. Well, there's a couple ways to assess this, right? You could just guess what you think it is, intuitively, yeah. You have 8 divided by infinity. Well, you can't really do that. You can't say 8 divided by infinity, and your calculator's not really going to do it either, right? But what you could do is you could test a big number. Like, 1 million or something. Or you can even go bigger than that if you like. All right. Probably don't need the calculator to do this, but just to be dramatic, I'll do it. 8 divided by 1 million. Zero 0.00000. Oh man, I have a hard time counting all those zeros. It's 6 zeros if you include the 0 to the left of the decimal. It's a neat trick with multiple powers of 10. So if this had 100 zeros, I'm not going to do 100 zeros, but let's do 9 zeros. What's that? A billion? Yeah, it's a billion. Then 8 divided by 1 billion would still have 9 zeros, but you have to count the one that's to the left. So I don't really need my calculator for all of these. It's one of the reasons why we group them in threes. So that's 3, 6, 9, and then an 8. Yeah. So what's happening is this is getting very, very close to 0. At some point, depending on what brand and the memory of your calculator might actually give you 0 as the result. Now, since 0 is a real number, we don't have to say it's well, I mean, it is approaching it, but the limit is equal to 0. And again, I mean, it is approaching zero, but because of the definition of a limit, if it's close to it, then we say it equals it, right? I should make a note. F of infinity does not exist. So you can't actually plug in infinity, but you could say that it's getting very close to infinity. Right? And so therefore the limit is getting very close to zero. Similarly, if I do negative a million, is that a million? Yeah. I'm just going to get negative 0.00008. And if I do negative a billion, instead of a positive a billion, I'm going to get negative. I'm just going to get the same value, but it's going to be negative. It's still very, very close to zero. It's just negative. So, as x goes to negative infinity, it is still getting very close to zero. All right. Let's see if a graph paper is coming. I feel a graph coming, but I'm not quite ready to break out. I got my graphing board here ready to go when I need it, but not quite ready to break it out yet. I'm just going to kind of do a very rough graph. All right. You can plug in 1, and you will get 8. Right? So I could evaluate this function if I wanted to get some dots. You could plug in 8, and you will get 1. Right? It's one of the reasons why it got its name, reciprocal. Yeah. So it's a reciprocal value. So as x gets larger, so if you plug in 8, you get out 1. Right? And vice versa, if you plug in 1, you get out 8. Right? You see the idea? And so this is what the function looks like, at least in quadrant 1. Similarly, if you plug in negative 1, you will get out negative 8. And if you plug in negative 8, you will get out negative 1. So it looks like this in quadrant 3. Again, I'm saying if you plug in, this is a very simple function, so I'm sparing you the board space here of writing it. But I mean, I hope everybody can see that out there. If you divided 8 divided by negative 1, you would just get negative 8. Yeah. And vice versa. If you did 8 divided by negative 8, you would just get negative 1. All right. So this graph has asymptotes. The vertical asymptote, x equals 0, and then it has a horizontal asymptote. We'll call that an HA of y equals 0. All right, so that's the basic idea of a reciprocal function. Now, I think a theorem is in order, right? A theorem is in order because we don't want to have to plug in large numbers every time. We don't want to have to draw the graph every time, but I do have my graph board if it becomes necessary, and it might. Let's come up with a theorem, or let's illustrate a theorem. A reciprocal function limit at infinity. And I should probably mention that whenever I give a a theorem about infinity, I really mean both sides of infinity, so negative and positive. I just don't want to write that. So if c is a constant and n greater than or equal to 1 is an integer, then the limit as x goes to infinity of c over x to the n is always equal to 0. Basically, when you think about this theorem, it means that you have a constant in the numerator and you have a power greater than 1, greater than or equal to 1, then the limit is going to go to 0. And so is the other limit. So both of these limits are going to go to 0. Negative infinity and positive infinity, they both approach 0. So there is a horizontal asymptote at y equals 0. There's also a vertical asymptote, but the vertical asymptote is from a different lecture. It's when you divide by 0, you get the vertical asymptote, but when the limit is approaching 0, so x is approaching negative or positive infinity, the limits are 0, that's the horizontal asymptote, which is going to be a main focus of today's lecture. So let's, again, it's much like the polynomial theorem. This is for reciprocals. We can apply this to a great many functions. This example is so straightforward that I can squeeze it down here. The limit as x approaches infinity of negative 7 over x to the 4th. Sometimes the negative will be out in front like this, but that means the same thing as this. There's your constant, negative 7. There's your power, which is greater than 1. Greater than or equal to 1. Then this limit is equal to 0. Okay. And there's a horizontal asymptote. Sometimes just abbreviate that HA. This is sort of the y value. It's not an actual point, though. So we say the asymptote is y equals 0. It never actually hits y equals 0, at least not for this particular type. All right, they'd have to get a little bit more sophisticated to actually touch. Similarly, the limit as x approaches negative infinity is also equal to 0. So you get 2 for the price of 1. All right, it's time to dig in and do a little more detail. And in order to show more detail, for example, 8, I've got a little bit more complicated function here. Negative x plus 3 over x plus 1. All right, so I have a negative and I have a reciprocal, but this time I've got variable in the numerator, not a constant. All right, so I got to be a little more careful. Let's draw the graph. And then evaluate the limits, or find the limits, whatever. Same thing. And now I'm gonna do several different types. Coming soon. I don't know what to say on this tiny board here. I mean, I could write them all over here on the sidebar here, but we'll see. Okay, let's get out the graphing board. Let's see if I can squeeze this in here. One thing I do when I'm graphing these functions is I like to rewrite the function. So f of x is negative x plus 3 over x plus 1. And I'll show you all the points and the limits and such as we move along. All right, now if you've had algebra, you hear me say that a lot, so you get sick of me saying that. I'm almost sick of me saying it, but I never know. I never know where people are coming from or even how long it's been since you had algebra. So this is a very common type of question. First thing I like to do is rewrite this as negative 1 times x plus 3 over x plus 1. Normally, I put my negatives up in the numerator. Again, that's not a mathematical law. It's just a convention to keep track of where it goes. You can't put it in both. You have to pick. All right, and if I have to pick between the numerator and the denominator, I usually go to the numerator. So this is going to be negative x minus 3 over x plus 1. So I like to simplify my function. Sometimes it's already written in simplified form. That's great when that happens, but it just helps. You ever see call it a floating negative out in front? It can easily be ignored or disregarded, and you'll end up wasting a whole bunch of time. So I just like to clean it up, get it in there with the rest of them, and then now I've got a good thing to work out. All right. So let's do the limit as x approaches negative 1 from the right. All right, so here's the following limits that we're going to evaluate. I guess I could have written them over here earlier. I wasn't sure if my head was going to get in the way. All right, I'll fit as many as I can. All right, this is a little bit of a review, right? This is a one-sided limit as x approaches negative 1 from the right. All right. So as x approaches negative 1, what's happening? Yeah. Negative 1 from the right. So something just a little bit smaller than negative 1. So I'm going to blow up my scale a little bit here. So 2 blocks. So these will each be half blocks, and then that'll be negative 1. It'll make it easier for you guys to see. And then this will be positive 1 and positive 2, etc. All right, so as I approach it from the right, yeah, I've got something like negative 0.9. Yeah, I really only need one test point. One test point. I can't actually plug in negative 1 because that would cause division by 0. Yeah. So maybe I should notice the limit as x approaches negative 1 is dne. Yeah. It would come out to be negative 1 minus 3 over negative 1 plus 1, which is negative 2 over 0, which does not exist. So I know there's an asymptote here. We call that a VA. Yeah. In the last video, I called that case 2. Yeah, the vertical asymptote case. Right? It's a constant divided by 0. That's a vertical asymptote. But what I don't know is whether it's going up or down. Yeah. So if I plug in a number very close to negative 1, yeah, I can't actually plug in negative 1 or I'm going to get dne. So I'm going to plug in a number very close to negative 1. Negative 0.9 into the x. You can use a calculator. It's probably going to need it. These decimals. I don't know. Do I really need it? This would be 0.1. And then this would be negative 2.1. All right. So double negative becomes positive. 0.9 minus 3, negative 2.1, divided by 0.1 is 21 negative. Get negative 21. I don't really care that it's 21. I just care that it's way down here. Oh, shit, I got off the screen here. I did this in the last video. I don't really want to count all the way to negative 21. And I really don't care. I just know that it's going down. The limit is going down. It's approaching negative infinity. So my answer is this approaches negative infinity. All right. And I'm going to stop this I shouldn't call it nonsense. I'm going to stop saying that. I'm just going to say it equals negative infinity. All right. Had enough, right? There's a couple of reasons for that. One is that I don't want to constantly have to go back and forth between is it equal to that or is it approaching that? Well, I mean, every single time you take a limit, when you say it equals something, it never really actually equals that, right? I mean, unless it's a point that's in the domain, right? But when it's not an actual point, there is no point in this. There's no point in the domain. Yeah. I should also mention that if you plug in 0, evaluating at 0, you're just going to get negative 3. So I get a dot right here at negative 3. I know my scale is not that great. And if you plug in positive 3, really need a lot of room. If you plug in positive 3, oh, wait a minute. No, not positive 3, negative 3. If you plug in negative 3, so these are points that are actually in the domain. You get 3 minus 3 over negative 2, which is 0 over negative 2. Now that does exist. That's 0. So we have some dots here. So we have one limit. We know the limit on the right is going down to negative infinity. And again, my scale on the y-axis is not exact. I went from negative 3 all the way to negative 21. It's very difficult to have a good scale. I should probably just erase that negative 21. So we know that as you approach it, it's going down, 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 like that. All right. Now let's find the limit as x approaches infinity. Let's find out what's going on here of f of x. Okay. So again, we don't know what's happening. We can't actually put infinity in here, but we can plug in. We have 2 dots so far. Yeah. I plugged in 0 and I got negative 3. I plugged in negative 3 and I got 0. So we do have 2 dots. If I was really confident, I could probably finish the graph now. But this lecture is on limits, so I want to continue talking about limits and then finish the graph. All right. What's happening as x goes to infinity? Yeah, you can kind of see Yeah, it's kind of leveling out here. But let's see, where is it going to level out at? Well, just plug in a big number for x. You don't really have to do 1,000,000, by the way. 1,000 will do. So that's going to be negative 1003 divided by 1001. Right? You don't really have to do this on your calculator, but I think you'll know what's going to happen. If you take 1003 divided by 1001, you get 1.001, blah, blah, blah. Yeah, so this is approximately 1. So this limit is equal to 1. Sorry, negative 1. I forgot the negative. I told you. Be careful with the negatives. As soon as I looked at the graph, I realized it was negative 1. So that means there's a horizontal asymptote at y equals negative 1. And now I can finish the graph. This is going to approach the asymptote here and approach the asymptote here. With the graph complete, I can find all of the limits. So the limit as x approaches negative 1 from the right is negative infinity. The limit as x approaches negative 1 from the left is positive infinity. All right. I know it has to be positive infinity because I'm going to get positive numbers out when I plug in numbers to the left of negative 1. It can't come back down here and be negative again. So all of these values, once you hit 0, all of these values are going to be above 0. It's going to go up to positive infinity. I could confirm that by plugging in a couple more numbers like I did on the right, but that took a long time. All right. The limit as x approaches negative 1 does not exist. So from the left, it's infinity. From the right, it's negative infinity. So the general limit does not exist. However, these limits do exist. The limit as x approaches negative infinity is also negative 1. So we have two limits at infinity. One of them, they're both equal to negative 1. That's the horizontal asymptote. All right. So that is what we call a rational function based on the same concept as a reciprocal function. The graphs are very similar. There are some variations in the coordinates and the shifting of the asymptotes, but generally speaking, it has this same basic shape. Okay, got some time to dig into the examples. And we will do example, I guess we can call this one 8, right? This was 8. Just want to remind myself where I am. We'll do 9, 10. I don't know how much more I can do today, but we'll do as much as we can here. Take a good look. Wasn't very well organized, but I've got 1, 2, 3, 4, 5 different limits that I did. And then I also identified the asymptote, the horizontal asymptote. Before I erase this, I know I wrote it earlier, but this one here is the VA x equals negative 1. So that's your vertical asymptote. So the vertical asymptote passes through the x-axis at negative 1. The horizontal asymptote passes through the y-axis at negative 1. Notice I'm using different scales. I wanted to exaggerate the scale a little bit, so my x and y scales do not match. Right? Look, I'm calling this -1 on the y, but I'm calling that -1 on the x. Mainly because my screen is not big enough to show the true scale. All right, that one's done. I like graphing, and graphing is very important in this course, but notice it took a long time to get this done. Without the graphing, if I just do pure algebra, the time is better spent and not quite as exhausting. So how about the limit as x goes to infinity? So the rest of these, I'm just going to do one limit, just to kind of get the idea out there, of 7x minus 15 over 3x squared minus 7x plus 5. Two things I want to avoid. I want to keep graphing, and we will keep graphing. You know, I bought this board, and there's a lot of graphing in the textbook, and when we get into the applications, it's nice to see a visual representation of what you're actually solving. So there are some good uses for graphing, but I'm going to avoid it for the rest of this lecture. So that's the first thing, right? Not that I don't like it, but it takes a lot of time. And then another thing that's very important in this course and also takes a lot of time is making tables of values and plugging in numbers. In the last example, I was very sort of loose with it. I just sort of threw some numbers out there, and I didn't make an organized table. That might become necessary again, but just not today. I want to use pure algebra to find this limit, right? And so I want to keep in mind just one idea as I do this. Anytime I have a limit, now for this example, I'm just going to do 1, just infinity, but this would also apply to negative infinity, of a constant over an x to some power, I automatically get a 0. Yeah, I keep that in mind. That's my goal. So let's use algebra to do this. Yeah. Let's divide everybody by the largest power of x, which in this case is x squared. And that will sort of force this to happen. So I'll have something like this. A constant over x squared, and then that will be equal to 0. Yeah. It's not always going to be x squared, but in this example it is. So I'm going to say this is equal to the limit, as x goes to infinity, of 7x over x squared minus 15 over x squared, 3x squared over x squared, 7x over x squared, and 5 over x squared. So I'm dividing all the terms by the largest power of x. And watch what happens. I really could have done this in the last example, but it wouldn't have been quite as dramatic. So I wanted to save it for when you actually have a power bigger than 1, right? When you do it with 1, I mean, the same thing happens, but the purpose was to show you the hard way, the sort of exhausting way, and then to show you the algebraic, you know, sort of emphasize the power of algebra. And sometimes, you know, you might even see some beauty in this. So 7x divided by x squared is 7 over x. 15 over x squared is just 15 over x squared. 3x squared over x squared is just 3. 7x over x squared is another 7 over x. And then that one stays 5 over x squared. All right. And now we're going to apply the limit to each one of these terms. All right. So the limit of 7 over x is 0. So by the way, this is true for x squared. It's also true just for x. Right? A constant over x is still equal to 0. A constant over x squared is also equal to 0. Now this constant does not have an x, so that one is not 0. That one's 3. And then these next two both have an x in the denominator, so they are all 0. So the limit is 0 over 3, which is equal to 0. The limit is equal to 0. And again, if I had 15 minutes to kill, I could break out the graphing board and I could graph a horizontal asymptote at y equals 0. It'd be like the dotted line right on the axis. So much faster when you just use algebra and you don't spend a lot of tedious time calculating and plotting and all of that. So this is the algebraic technique for evaluating limits at infinity. Take another example. X squared plus 15x minus 2 over 4x squared minus 3x plus 8 All right. So we're going to divide all of these terms by x squared. Again, that's the largest power. Now I'm writing every step. You could probably do the division mentally and then just jump right to what it is. You can get away with that with some of the simpler problems, but as they get more complicated, having the step-by-step method can really assist you in preventing mistakes. When you've seen me make mistakes when I get lazy and sloppy. So you could have done all that mentally and then jump right to here. This one's pretty tame. So you're going to get 1 plus 15 over x minus 2 over x squared. Then you're going to get 4 minus 3 over x plus 8 over x squared. So that's going to, and then again, you apply the limit. Again, I am being lazy now. Technically, what I'm doing is I'm doing 6 different limits. So the limit of 1, but now we're getting to, a level where writing lim 6 times is really not going to help the problem out. It's not going to help us calculate it. Just, think of it like you're distributing the limit. Those are the properties. I am free to do that. And then 0 and then minus 0, yeah? So anytime I have a constant divided by x, or x to any power, those are all going to be 0. And then 4 minus 0 plus 0, which would be 1/4. All right, so that's the idea. Maybe I could do 2 more. If I could get 12 in today, that'd be great before my time runs out. Example 11. So I've got 8x cubed plus 2x squared minus 4 over x squared plus 9x plus 1. So this time the largest power of x is x cubed. So I'm going to divide everybody by x cubed. It takes me longer to write all this down than it does to actually compute it, but nonetheless, we're going to do it. So 8x cubed over 8x cubed is just 8. 2x squared over x cubed is 2 over x. This term stays the same, 4 over x cubed. X squared over x cubed, that's 1 over x. 9x over x cubed is 9 over x squared. And then this term stays the same, 1 over x cubed. And then I'm going to apply the limit 6 times. Oh, it's 6 again, yeah, 6 different terms. And I'm going to get 8 plus 0 minus 0 over 0 plus 0 plus 0, which is 8 over 0. Now be careful. If it was 0 over 0, it would be indeterminate. Case number 3 from before, which might come back and haunt us later, but it's not. It's a constant divided by 0, and that's not an indeterminate. We know that that does not exist. So this limit does not exist. Now, does it go to infinity? Does it go to negative infinity? I don't know, right? We just know that it doesn't exist. If I wanted to know whether it goes to infinity or negative infinity, I'd have to do a little bit more research, right? My guess is that it's going to infinity. That's my guess. The leading term is positive. I could sort of modify my polynomial rules. This is not a polynomial. This is a rational function. It's the ratio of two polynomials. But these things get a little more complicated than the polynomials. They're not quite as straightforward. So I'm just going to say the limit does not exist. Right? I don't know what it approaches, right? But I could get to that in the last example. In the last example, I'm going to illustrate how you can put all this together to find a limit. I'm not going to do any more graphing, though. So I'm just going to do one more sort of exhaustive version of this. Maybe not so exhausting, but larger version. That's a better way to say it. So find the limit. We got 9 minus 8x plus 5x to the third minus 7x to the eighth over 7 plus 5x minus 8x squared plus 9x to the sixth. Not much larger. It's really just the same concept. In the interest of time, I'm going to talk my way through the dividing step, as I presume many of you will do. So this is sort of the quick way. As long as you're careful, you can get away with this. So the largest power is x to the 8th. Identify this. Notice this is not written in descending order. This is written what's called ascending. It's getting larger as you go from left to right. So the largest power of the entire expression is x to the 8th. So let's divide everybody by x to the 8th, and let's do it very efficiently. Notice that the powers will get reduced. So that one will become 7. This one will become 5. 5 over x to the 5th. And then that one will just be -7, because when you divide it, the x to the 8th will go away. This one will be 7 over x to the 8th. 5 over x to the 7th. -8 over x to the 6th. And then 9 over x squared. So generally speaking, if you're doing a lot of these, you want to have a way of dividing mentally and then writing down the result, so it saves you a little bit of work. If you miss one, you might wish you would have written it all down. All right, so what is that? Again, if I was being very pure, I would write lim that many times, but I'm not. I'm just going to do it. So this one is 0. That one is also 0. The next one is also 0. -7. 0. 0. 0. Oh no, we got all zeros. Or you could say, good, I'm glad we got all zeros in the denominator. As long as the numerator is not 0, you can stop, you get a free answer, and you just say DNE. All right? I've really run out of time. Next time we'll dive more deeper, probably less quantity, a little bit deeper into the behavior. We know this limit doesn't exist, but I want to pull it back to, is it going up? Is it going down? I want to talk about the asymptotes. There are 2 different types. Until we meet again, I'm Dr. Jordan, and I'll see you on the internet.